Right, in this video, we're going to be looking at organic geochemistry, specifically a topic which is not always discussed, that is organic matter diagenesis. Why do I say it's not always discussed? Because when you say diagenesis, everybody thinks about changes that takes place in a rock. But this case, we are going to look at changes that takes place to the organic matter in sediments. So the changes that takes place to the organic matter in sediments is known again as organic matter diagenesis. What is diagenesis? Diagenesis in the context of organic matter. Okay, be very careful. We are talking in the context of organic matter. Refers to biologically induced changes in the organic matter composition that occur in recently deposited sediments. Now, whether these sediments are deposited on land or in the nearshore environment or in deep marine environment, it is not that issue. The issue is that diagenesis, especially organic matter diagenesis, can take place here or even here or even here. That is right. It can take place in the presence of oxygen and in the absence of oxygen. That is not a problem for this organic matter diagenesis. Now, on land, we know that, for example, bacteria plays a very important role in the carbon cycle, nitrogen cycle, and sulfur cycle. Now, we're not going to go through this in detail, but if you look at the right-hand side, you'll find that in the atmosphere, you will have aerobic respiration. Below the surface of the soil or sediment, you will have a steady depletion of oxygen. Therefore, you will start to have nitrate reduction initially, a little deeper, sulfate reduction, and last but not least, methanogenesis, in other words, formation of methane. Now, it is not the objective of this particular video to teach you how methane is formed, but if you look at this particular section, okay, you will notice that you can have acetogenesis, in other words, the formation of acetate, okay, and through carbon compounds, given the right redox potential, which is abbreviation for reducing oxygen potential, reducing an oxidation potential, you can have the formation of methane, which is CH4. The process of forming methane is known as methanogenesis. You don't have to worry yourself about all the other processes, but if you're interested, you can always have a look at it. Now, once the organic matter is embedded in the sediments, these are pieces of minerals, okay, and you have organic matter in between them, or even coating those minerals, doesn't matter. What is the fate of this organic material? Very little attention has been paid to this. Now let me tell you, it is known for a fact that functional groups such as carboxyl, amines, and hydroxyl are preferentially removed from their parent molecules. There you go. That's the first removal that's going to take place. All the functional groups are going to be taken away from your organic material when they are in sediments. This can happen before the organic matter is preserved. Okay, before it is preserved, you can have the removal of functional groups. This is very important because chemical reactions depend a lot on functional groups. So the laws of functional groups such as COOH or C double bond O single bond OH and OH decreases the oxygen. Okay, because you have a lot of oxygen here and here. When you remove this, basically you're losing oxygen. And to a lesser degree, the hydrogen which is associated here and here. Therefore, you have lost oxygen and hydrogen in the contents of organic matter. You have to remember this. By and large, the oxygen and hydrogen can be lost in the organic matter in sediments before anything else takes place. Next, the abundance of readily metabolized organic compounds decreases. For example, nucleic acids and amino acids and related compounds appear to be the most labile. In other words, they can move a lot and therefore they are most readily destroyed. Followed by carbohydrates, particularly simple ones, and those synthesized for energy storage, example starch, rather than structural ones like cellulose. Okay, the simple molecules in these groups, for example, the amino acids and glucose, are most labile of all. Lipids appear to be somewhat less labile. In other words, they stay on for a little longer. So what do you gather from this? It's very simple. Okay. Besides the reduction of oxygen and hydrogen there, certain compounds are already going to be removed from the organic material. This is the first sign that the original signature of the organic material can be changed. Let's look at some more factors. The unsaturated compounds, by unsaturated we mean, okay, saturated means there's a single bond, for example, C and maybe another C or something else with something else going on there. Unsaturated compounds when you have double bonds or triple bonds, for example, which means that they can open up to form more bonds, okay? So unsaturated compounds decrease in abundance compared to their saturated equivalents due to hydrogenation of double carbon bonds. In other words, these bonds tend to disappear from the organic material because of hydrogenation. In other words, you're adding basically some new compounds to the compounds which can actually react. These are bonds which can actually react chemically. You modify them, okay, and you add something else to it. Therefore, the ability of the organic material to chemically react now is reducing further. Next, aliphatic compounds decrease in abundance compared to aromatic compounds. What are aliphatic compounds? These are light molecular weight material, whereas aromatic ones are the heavy molecular weight compounds. This is light and this is heavy. So aliphatic compounds decrease in abundance, okay, partly because of aromatization of unsaturated aliphatic compounds and partly from more resistant nature of the aromatics. In other words, aromatics can test the stand of time, they are strong, whereas aliphatic change very fast. Okay, this is one reason, but I must tell you there's another reason also. Aliphatic compounds being lightweight molecular compounds, they are more labile than aromatic compounds. So because they can move, sometimes you just lose them. They just move out. Now, short-chained molecules, example alkanes and fatty acids, decrease in abundance relative to their long-chain equivalents. Now, this is the same thing, echoing from above. Since the aliphatic are reducing and aromatic is increasing, well, basically the short-chain molecules, like alkanes and fatty acids, basically decrease for all the reasons they're there, and the long-chain molecules basically tend to stay back, and therefore it appears as if they are increasing. Okay, it appears as if they are increasing. Now, this relative differences in short chain and long chain, okay, if it is exemplified into the rock, which may retain all these products, it can deliver sometimes very confusing opinions to a practicing geochemist. Next, hydrolysis of complex molecules that produces a variety of molecular fragments that subsequently recombine with other molecules to produce new ones not present in the original biota. This is a very interesting statement. I don't want anybody to forget this. Okay, because of some chemical reactions, you could probably recombine some molecules to produce new molecules, okay, that never existed in the original material. So in other words, the signature can be tempered simply by chemical processes. For example, phytol produced by degradation of chlorophyll A and phenols which can be produced by degradation of a variety of aromatic compounds condense to form phenol-phytol compounds. So there you go. Did you realize that you can have so many changes in the organic matter in sediments before you have the formation of a rock? So in summary, in high sulfur environments such as marine sediments, addition of H2S produced by sulfate reducing bacteria ends up being incorporated into carbon double bonds in the long chain compounds such as isoprenoids, basically to give you thiol, which is standing for sulfur, functional groups, and these can subsequently form cyclic structures and ultimately aromatic thiophenols. Now, this process is known as natural vulcanization. Okay, natural vulcanization. All right. I think by now you should realize that many types of changes can occur in organic matter when deposited in sediments. Not everything, some of it, as discussed, or sometimes if you're really lucky, everything can happen to the organic matter. In most cases, if not all cases, redox or reducing oxidation conditions controls many of these reactions. Take note that typical typical signatures may be lost before the sediments become consolidated to give you a rock. Now, taking into consideration all these changes that can take place in an organic matter which is deposited in sediments, I would really like to ask you to think deeply as to what is the difference, okay, between the original organic material which is deposited and the organic matter which is in sediments which has evolved from this just before the onset of consolidation, or in other words, before the sediments becomes rock. Try to recall all the things that can take place, okay? All right. Now, I hope that you have enjoyed learning something about changes that can take place to the organic matter in sediments, as much as I have enjoyed teaching it to you. Look out for more videos on organic chemistry and happy learning.